to speak about a new world record about the so-called irrationality measure of pi. I will explain very soon. Does anybody in this audience know who the following person was famous for? Roger Bannister. Anybody know? Have you heard of Roger Bannister? Because you are too young. If you were even older than me, by 10 years, you would probably know it. Like, he was a very, very big thing. His claim to fame, he was the first person to run a mile under 4 minutes. So here is the list of the partial list of the world record holders of the mile race. The first record is 1852, was 4 minutes 52 minutes, 4 hours, 4 minutes 52 seconds. C. Marshall. Then 4:45, and some people they lasted several years, but some people the record was broken shortly after, so they were not world champions for very, very long. Then in 1945 was somebody called G. Hag, who ran the mile with 4 minutes and 1 second. And he was the champion for 9 years. And then Roger Bannister in 1954 was the first person to break the 4-minute barrier. And he was very famous because it was a milestone, no pun intended, in the mile race. But poor Roger Bannister, his record only lasted 46 days. That's the problem with world records. Sometimes they are broken sooner than later. A few years ago, I wrote a controversial quote-unquote article, what is mathematics and what should it be? And then I claimed that mathematics is anything except for science. First, mathematics, because scientists want to find out the truth about the outside world. Mathematicians don't really care about the truth about the mathematical world. They play their contrived, artificial, dogmatic game called rigorous proving. They want a rigorous proof. So many things are obviously true. The Riemann hypothesis that P is not equal to NP, and heuristic reasons. So I claim that first, mathematics is a religion. It's a religion that has its dogmas. But also, it's a competitive sport. People like to prove conjecture because they want to beat other people. And it makes the most obvious contest is the so-called irrationality of pi. So let me first remind you what does it mean for a number to be irrational. Of course, in the old days, only 2,500 years ago, Pythagoras, speaking of religion, now mathematics is a religion, but not officially so. It's not called a religion, it's called an academic subject. But 2,500 years ago, about somebody called Pythagoras made numbers and mathematics into a real religion. And they worship numbers. And they believed that integers are good numbers, are sacred. And even ratios of integers. If A is an integer, the ratio, that's a good number. 2/3, 5/8, 11/, whatever, are all numbers. And they believe that all numbers are quotients of integers. Then came some wise guy called Hippasus of Metapontum and proved, quote unquote, that square root of 2 is not rational. And he was wrong. Square root of 2, he didn't disprove that all numbers are rational. What he proved is square root of 2 is not a number. But suppose it is a number, the proof that you learn in the high school, and no, probably in Math 300, is a stupid, boring proof. It's a proof by contradiction. And it's very indirect and doesn't give you any insight. But anyway, there was the first crisis in mathematics that some numbers are not rational. It's surprisingly difficult to prove that any given explicit constant is irrational. E is not too bad. E is an exercise. Euler proved it, but you can prove it too. But pi, the most important number that is not algebraic, even more important than E, no offense to E, pi, took much longer to prove that it is irrational. Does anybody know who was the first person to prove that pi is not a fraction? Huh?
Lindemann.
No, Lindemann came out later. He proved that pi is not algebraic. And it is so-called transcendental. But Lambert proved that pi is irrational. This was in 1761. So Lambert was the first one to prove that pi is not a fraction, is not a ratio of composition. It was the first one. But his proof was also stupid and boring, similar to this. Proof by contradiction. Where he proved, suppose, that x is rational, then tangent of x is irrational. That's what he proved. If x is rational, and the proof is pretty nice, this part is quite nice. It's nice continuous fraction, and it is nice. But the corollary of this theorem, that pi is irrational, is not nice because it's a proof by contradiction, and it's not constructive, and I really don't like. So proof by contradiction. Suppose that pi would have been rational, then rational over 4 is still rational. So tangent of pi over 4, as I hope you know, is 1. And as far as I know, 1 is rational. Contradiction, so it's a proof by contradiction, not very nice, but it's a proof. So that was, going back to Greece, one of the 3 famous open problems, as I'm sure you know, was squaring the circle. Can you find with compass and ruler the dimension such that x squared equals pi? In other words, we have to find a way of constructing the exact length of square root of pi. And it's easy to prove, well, not, that every quantity that you construct by compass and ruler, the Greek way, ruler without marking of course, must be an algebraic number of a special kind. The degree has to be a power of 2, but never mind. In particular, if you can prove that pi is not algebraic, if pi is not a solution of any algebraic equation, then you have proved the 2,500-year-old Greek problem about squaring the circle. And 24-year-old Lindemann, using the previous ideas of Hermite proved that E was not algebraic, it's called transcendental, and proved that pi is not algebraic, so pi is transcendental. But once again, his proof is not satisfying. Once again, a proof by contradiction. What he proved, the Hermite-Lindemann thing, is that if x is algebraic, implies that e to the x is algebraic. So if pi is algebraic, then I times pi is algebraic. So e to the power I pi is negative 1 is also transcendental. Sorry, x is algebraic implies e to the x is not algebraic. Sorry. If x is algebraic, then e to the pi x is not algebraic. So proof by contradiction. Suppose that pi is algebraic, then I times pi is also isobric, because so e to the I pi would have been not isobric, but minus 1, as you know, is isobric, so QED. So this is the transcendental. But we're not talking about transcendental. A much nicer proof of the irrationality of square root of 2 is the following. Use maple. Or for the sake of example, to make it even easier, suppose I want to prove that the golden ratio is rational. A much nicer proof than the usual proof. Constructive proof. This is the golden ratio, the famous golden ratio. Go to maple and ask it to do convert it to a continued fraction. And lo and behold, you get 1, that's 1, that's 1. Of course, you can also do it by hand. Ad infinitum. Of course, maybe only does it to a finite number, but you can easily conjecture. So that's a conjecture. So how to prove that this is actually equal to phi, the golden ratio? You call this x, for example. Then x is self-similar. X is 1 plus 1 over, and this is x once again. Infinity minus 1 is infinity. So you have x equals 1 plus 1 over x. Here in numerator, x squared equals x plus 1. Now use the formula for 9th grade. 1 plus or minus the square root of 5 over 2. But it is positive, so x equals this. So this is, and since it's an infinite continuous fraction, it must be irrational, because it's very easy to see the Euclidean algorithm. If you have a finite, if you have a rational number, if you do the continuous fraction, it's finite. This goes forever, so it's unproved. But you can get much more information from this thing. Let's truncate it after n steps. So let this be with n. So now it's a rational number. And let's call it a sub n over b sub n, the so-called approximants. There are finite approximants for the golden ratio. So what do we have? A sub n over b sub n equals 1 plus 1 over, now it's not infinity, now it's n minus 1. 1 over a n minus 1 over b n minus 1. Simplify, 1 plus b n minus 1 over a n minus 1. Simplify some more, a sub n minus 1 plus b sub n minus 1 over a sub n minus 1. Equate and get a sub n equals a sub n minus 1. And bottoms, b sub n equals a sub n minus 1. But if b sub n is a minus 1, then a sub n is a minus 1 plus a minus 2. And the missing conditions are a1 equals 1 and a2 equals 1. And since bn is a minus a, since an, yeah, so we have the approximation n minus 1 over an. But this should then gewähren, these are the famous Fibonacci numbers. So we have good approximations, terrific approximations for the golden ratio f sub n plus 1 over f sub n. In particular, so now we have f sub n plus 1 equals f sub n plus fn minus 1. F sub n equals f sub n minus 1 plus f sub n minus 2. Multiply this by f sub n. Multiply this by f. And sure enough, we have the difference between two consecutive approximations. And this is Hasidi's. We shall only can do it in one instant. This is called Hasid identity, the basis. So it was 1 over. Now it's easy to see that the f sub n's are exponential growth. So if you do it, you get the following fact. The sequence of rational numbers approximating the coordinate ratios, which is really f sub n over f. Sorry, f sub n plus 1 over f sub n. It's easy to see. It's bounded by a constant, in this case 1, over f sub n squared. And this was the key thing. And let's do for every quadratic irrationality. And the similar proof. But this gives a motivation for a technique, a way, a strategy to prove that the candidate constant is irrational. Come up, so input some number x, hopefully famous, so people get interested in it. Strategy for proving that it's irrational. Come up, construct explicitly a sequence of rational numbers. So we have top and bottoms, an numbers, a sub n over b sub n, such that x minus a sub n over b sub n in absolute value is less than some universal constant c b sub n of 1 plus delta. In this case, delta is 1. That's the best you can hope for. But even if delta is 0.0000000000001, you'll be world famous if you make it. Homework problem for you. Do this strategy for the following to-do list. Euler's constant. This you can define as a limit of the difference between the harmonic sum and log natural, but maybe a better way is in terms of this integral. Wide open. Nobody has any clue how to prove it. Of course it is irrational. The saying that it's rational is much smaller, that I am just in the dream of some giant. It's obviously, that's why mathematicians are so fanatic. They say, we don't know yet whether gamma is irrational. Of course it is. We don't know how to prove it rigorously using the paradigm of rigorous proof. But this is a nice game. It's a sport. It's a very nice, challenging game. Like selling a chess puzzle made in 100 moves. But it's still this. So this is the first to do this. Homework problem for you. The other one that is probably most hopeful is the Catalan Constant. 1 minus 3 squared plus 1 over 5 squared. So it's the alternating sum of the reciprocals of the odd integer. Nobody has any clue how to prove it. Good luck. Next in line is zeta 5, sigma 1 over n to the power 5. And similar for all the zeta 7 and so on, also zeta. That's the to-do list. Even more basic, nobody has any clue how to prove that e plus pi is irrational. Of course, there's no reason why it should be rational, so it is irrational, but nobody has any clue how to prove it. Nobody has any clue how to prove it e times pi. Yes. But exercise for you, prove that not both of them can be rational. This is not too hard. So this is the to-do list for irrationality. So this strategy of coming up with explicit things goes back at least to Euler. The only problem is how to construct this sequence of approximates. And by the way, if data is negative, for example, if data is minus 0.0001, it won't be a famous number theorist, but it's still very interesting numerically, because b sub n is an exponential growth. So the error is exponentially small, shrinking. So it's still interesting numerically, but it's not interesting number theoretically. So this was the strategy. And E was basically similar to the proof I gave you for the Gaussian ratio. It's easier to talk about E minus 1 over E plus 1. Then also there is a nice infinite continued fraction. 1 over 2 plus 1 over 6 plus 1 over 10. So now it's no longer, now it's increasing. It's a linear thing. But basically, similar proof, a little bit more complicated, proves that you can do with E, or rather this, delta is 1. Now, there is something called the irrationality measure of a number. And the irrationality measure, one can come up with a specific sequence A sub n over B sub n, and a specific C and delta, so the delta is positive. Then the so-called irrationality measure, for which my collaborator Vadim Zudilin and myself broke the world record, I'm going to talk about it soon, is 1 plus 1 over delta. So if delta is 1, the algebraic case, and also E, the rational method 2. And that's the best you can hope for, the rational method 2. For most, and this was also used by Liouville before Lindemann, famous, and before Hermite proved that E was transcendental, and later Lindemann proved that pi is transcendental. Liouville proved that there exist transcendental numbers. Before they didn't even know whether transcendental numbers exist. But he constructed some artificial numbers, Liouville numbers, that are obviously not algebraic. And that's how he proved it, that the delta is very, very, very big. Anyway, so this is how it goes. In 1978, okay, so proving that the famous constant is irrational, and the constant is famous enough, for example, Catalan Constant, or gamma, or E plus pi, will make you immortal. But once the number is already known to be irrational, it's still interesting to find irrationality measures. So for pi, it was not known whether there exists a finite irrationality measure. So that's how another contest started. Pi is already known to be irrational, proved to be irrational. But can you do an explicit constructive proof with an explicit delta irrationality measure? So that was the other contest. Make it a competitive sport. So let me list, the analogous list. By the way, today's record of the mile that lasted for 10 years, I think. Oh, only 20 years. So it's a long list. I got it from Wikipedia, of course. Right now, today, the current record of the mile race is 4 minutes, 43 seconds, and 0.13 by somebody called H.E. Rouge. So he is a current world record in the mile race. Now let me give you the list of the record holders in the irrationality measure of pi. So the idea is with pi, come up with explicit sequences of rational numbers a over bn such that delta is as big as possible, and hence this is as small as possible, and the limit is 2, and probably the true answer is 2. That's probably the answer, but nobody can prove it. For E it's easy, relatively easy, but for pi you need to work hard. The great number theorist Kurt Mahler was the first one, so it was still an open problem to prove that delta is finite, because the proof by Lambert and Lindemann was not constructive. So to find an explicit thing, and Kurt Mahler in 1953 has a record of 42. He was very happy to be the world champion for quite a few years. But then in 1974, I don't know if he was still alive, Maurice Mignon, a French number theorist, found a better record, 20. And this was the world record for 8 years. In 1982, the great number theorist, Gregory Chudnovsky, he was famous for his pi studies, got the following record, 19.889944. So he had to work very, very hard, 30 pages, to get the, it's like running a mile and getting 1 second faster, and that's a new world record. So the gap is so small, but still it took 8 years, and somebody is smart, and Gregory Chudnovsky to break the record. The next record was much later, 1993, by a brilliant Japanese number theorist, Masayoshi Hata, I think, M. Hata. And he did something more substantial, 13.398. But his record didn't last long, poor guy. This was broken a few months later and became 8.016045. Lucky for Professor Hata, he was the same one. He broke his own record. So he cared, he wanted to make play safe. So he broke his own record shortly after. And that's how things stood for 15 years. In 2008, the brilliant Russian number theorist Vladislav, Kazanov Salikov. Broke the record 7.60638. Now I have an etiquette question. I have a question. Somebody who knows Russian and may be familiar with this. But he's asleep. Is it ethical to wake him up? What do you think? Okay, go on. So this has things stood until in 2019, December 2019. Two brilliant mathematicians. One of them a professional number theorist, the other one is an amateur number theorist, but a professional experimental mathematician. Zandberger and Zudilin. Johann Zandberger and Vadim Zudilin found a new world record that hopefully will last for a while. At least as far as I know, it hasn't been broken. And the current record is 7.1003341337. Of course, we know that this is the current record, and we are very proud of it. So it was the competitive sport. It's a funny motivation for this collaboration. We did not, when I contacted Vadim Zudilin, I did not plan of being a world champion for this. As you know, my name starts with a Z. In the stupid convention of mathematics, then authors are listed alphabetically. And even I had a student called Anthony Zaleski, ZA. So even him, I had to be the last name also. So I said, for once, let me collaborate with somebody. So first we had some very almost trivial paper. By seeing one thing after another, we started collaborating, and we had 3 papers, much more substantial, and this is the most substantial one. So this motivation was just vanity, but it led to something significant. So this, let me explain the strategy. The strategy goes back to Euler, but I told you the strategy is to come up with explicit things. And the impetus for this was a 64-year-old Horacio Young, Roger Aperi. In 1978, somebody who had not published for many years astounded his colleagues by sketching a proof that zeta 3, the sum of the reciprocal of the cubes, is not rational. And nobody took him seriously. How come somebody who has not published for 20 years anything substantial all of a sudden can prove something so open? But he was right. And the strategy was exactly the same. To come up with a specific, explicit sequence of A sub n and B sub n. There was. And other people filled in the detail, and that's how it became immortal. By the way, zeta 5 is still wide open, and zeta 7 and so on. So zeta 3, an over pn less than or equal to 1 over b to the power n, b sub n, sorry. And the delta was roughly 0.08. So this 1 plus 1 over delta was 13 something. But in this case, he also found an explicit irrational measure, but the big deal was that it was a proof that it is irrational. But the A sub n and B sub n were very complicated. He was 64-year-old. So although mathematicians sometimes prove nice things. And what's really remarkable is that he didn't prove anything for the 30 years before. When he was young, he was very prolific. Maybe he was thinking about it all his life. Anyway, it was a good, heartwarming story. And all the mathematicians sometimes can make a breakthrough, contradicting Hardy's stupid statement, the mathematician is a young man. Or young man. Okay. But his A sub n and B sub n were kind of artificial, and then a young person, he was only a PhD student then, he was 23 or Boykers, Fritz Boykers. He came with a better way of defining A sub n and B sub n. He had a triple integral. Here goes. He defined this triple integral that for any specific n, Maple can do, although it will take it a long time, because it's a little bit complicated. The x to y dt. Consider this triple integral, I of n. It's an exercise by partial fraction or whatever to prove that you can always express it as a sub n minus b sub n times z3. That's an exercise. The problem is a sub n and b sub n are rational numbers, they're not yet integers. But it's easy to see because the inside, if you just bound it, this I of n is very, very exponentially small. It's tiny. So you get an minus bn, zeta 3 is tiny. So you divide by b of n, and you get tiny over b sub n. But the catch is a sub n and b sub n are not yet integers. But if you multiply by the least common multiple of 1 to n, cube both sides, then the integers, and then asymptotics washed out, and you still get. So it's the same, it's really a new way of doing a Paris proof, but much more transparent, with a single integral. So this works for 3 dimensions. Then the brilliant young mathematician in 1982, now he's not so young, Irrationality, and his collaborator, Michael Robinson, tried to find analog with one integral. So you have x to the n, consider the following integral. This is much simpler. And exercise is a of n minus b sub n times log 2. And using this technique, I don't have time to do the details, he found the best known irrationality, the first irrationality measure for log 2, which was 4 point something, 4.8. It has been improved since by Leibniz. So this was the trick. This kind of integral is not new. Let me quote a theorem that my 5th grade teacher told me. So once again, the same idea. If you write it like this, you find, you ask your calculus students, to find the maximum of this from 0 to 1. This is very, very small. So you bound it. So this is tiny. So this difference is tiny. So you get very good approximations to AN and BN. So you have A1 log BN minus log 2 is tiny. But you want to be also tiny from the point of view of number theory. And right now Bn is not an integer. But if you multiply by the least common multiple of 1 through n, which by the prime number theorem is e to the power n. So it's Bn tilde, then it still works out. Because this is asymptotically e to the power n exercise. Anyway, that was how he did it for log 2. So one-dimensional integrals are much easier to handle than three-dimensional and triple integrals, both conceptually and computationally. But then we quote the theorem for Mrs. Cohen, my 5th grade teacher. That's how I learned in 5th grade. That pi equals 22/7. That's what I learned in 5th grade. That's equivalent to this statement. So this is not quite right, but the difference is pretty small. And explicitly, it is the single integral is x to the power 4 times 1 plus x to the power 4. That's an exercise for you. You divide this by this, you get a polynomial, and then you get a rational number, and then it's really arctangent. So this is this. So this might suggest a way to find an irrationality measure for pi. This suggests the following integral as a candidate. Integral mu to phi. So there, yeah, let's put this. Yes, on. And you get terrific approximations, much better than 22/7 if you do this one. If you do this one, you get even better ones. But the implied delta is still negative. So it's not enough to prove irrationality or to get an irrationality measure. But Salikov V.K.H. Salikov, have you heard of him? Oh, so it's a number theorist, the Russian number theorist. Vodoslav Khavanovich Salikov in 2008. He came up with also an integral like this, but much more complicated and having complex numbers. But for the sake of convenience, it was a complex. But he made it real. It could be made real. So I don't have time to tell you exactly, but the same idea. Some complicated, but still from 0 a finite. For 4 minus a, doesn't matter exactly. Complicated. To the power n dx. And using this, the same approach, he found the previous world record. Then we looked at what he did, and the same methodology is naturally generalized to a whole family of thing. So it was unnatural, he didn't do it explicitly, but the kernel that enabled him to prove the rational method had implied parameters A and B. Then my beloved servant, Shalosh B. Echad, experimented with many A's and B's. So his study course was 2 and 3. So it turns out, if you do 3 and 5, you beat his world record by 0.5. And that's how currently, and hopefully for some time, Vadim Zudilin and myself will be the world champions in the sport, in the competitive sport of bounding the irrationality measure of pi. But if any of you will break it, I won't be too upset. Thank you very much. Any questions? Yeah. We have time for one.
Have you tried 5 and 7?
Yes, I try everything up to 15,15 or 20,20. Yeah, and you got slides. Very good question. So the Fibonacci are always good. So 2-3, 3-5 was better than 2-3, but 5-8 was slightly worse than this. It was still pretty good, and for some reason I don't understand why. I don't understand. And then 8-13 was also good, but not as good. So 3-5 hits the jackpot. Yes.
So does anybody have an idea to get a lower bound?
Lower bound, I don't understand.
Irrationality measure, no?
The lower bound is 2.
No, I mean 2 is by triviality when you think of 5.
No, it's most likely equal to 2.
Ah.
So if you're not like a mathematician, it is 2. So it'd be a crackpot if you prove it 2.5. Or no, it's possible logically, but it's unlikely. So that's a good question. It's extremely unlikely that the lower bound is not 2, but to prove it. So the game is to an upper bound, not a lower bound. Yeah.
Is that true of every irrational number, or like almost every
except for
irrational
artificial
number?
ones, like Liouville numbers that are artificially not. You can concoct them if you try hard. But anything, let's put it, anything naturally occurring. I don't like to talk about Aleph 0 and Mel 0, I hate this. But any naturally occurring constant, most likely it's 2. But to prove it is usually difficult.
So what could be the upper bound of the lower bound?
Right?
What could be the upper bound of the lower bound? Could it be?
No, the lower bound is 2.
No, I mean, you mean generally it should be 2, but there are some irrational numbers.
Yeah, like Liouville numbers, so-called Liouville numbers.
So, I mean, could the upper bound of the lower bound go to infinity? Whether you can construct a sequence of irrational numbers such that...
Yeah, for artificial numbers, not for natural numbers like pi or pi plus c. Okay, any more questions will be answered later in private. Thank you very much.